Hello and welcome to another Chemistry Unplugged video. This one's about nucleophilic substitution. As you can see, this is about another mechanism that pertains to AS chemistry, and there are two videos already on electrophilic addition. Now we're going to do nucleophilic substitution, which is different in two ways. One, it's nucleophilic, not electrophilic. And two, it's substitution, not addition. A nucleophile is an electron pair donor. So I have a definition: nucleophile, electron pair donor. I'm sure you've been told this already. An electrophile was an electron pair acceptor. So this is the opposite. So we need something with spare electrons. That's something to bear in mind. Donor. At AS, there are three nucleophiles to be interested in, or try and be interested in. There's OH minus. Now that would come from maybe sodium hydroxide, something like that. We've got CN minus, which is a cyanide ion. And finally, we've got ammonia. They're the three that we need to be looking at today. And you'll be pleased to know that the mechanisms are all so similar that it's not going to take us very long to go through this. So let's go. We'll use bromoethane, which is this, as you probably know. Now, the thing is, you need to draw bonds. You can draw all of them if you're not sure, but I've just drawn the one that's going to be relevant in this mechanism so that I can do a curly arrow. And please remember that a curly arrow is the movement of a pair of electrons in a covalent bond. That's all it is. Doesn't mean anything else. It's very rare that teachers actually tell you what a curly arrow is and what it's for and why it's curly. It's curly so it doesn't just look like a normal reaction arrow. Well, at least you know now. So we don't need to go through dipoles all over again. We've got a delta plus and a delta minus, as you will see from the earlier videos. And we'll choose the first nucleophile to get started. Nucleophile really means it's attracted to a part of an atom or a molecule that's positively charged. And even if it's only slightly positively charged. So that pair is going to go to there because the electrons are negative. That's positive, albeit only a bit positive. That's done. So we're going to make a bond between the oxygen and the carbon. And these arrows have to be very precise. They have to be in exactly the right place. We're going to break this bond. And what we end up with is we replace the bromine with an OH group. And that gives us an alcohol, in this case, ethanol. And of course, as before, we're going to get a Br minus. So that's all it is. And the Cn minus one, I won't even go through it because I can, well, I won't do it all. I'll rub out some of this. Hopefully you're happy with that now. So we'll get rid of the OH minus and we'll get rid of the Br minus and we'll use something else instead. We'll use the Cn minus. Right, it's a bit far away. All I need to do is make the arrow a bit longer, as long as it's curly. Be as curly as you like. So the carbon is going to make a bond with the carbon atom. So this time it's not going to be OH at the end, it's going to be Cn. So we'll get rid of that and that and stick a Cn on there. The other product, once again, is Br minus. And obviously that is no longer an alcohol, it's what's called, and don't worry about these, you'll see them again next year if you're in AS. This is a nitrile. And more specifically, it's ethane nitrile. Sorry, propane nitrile, because this carbon counts as well. If there's 3 carbons in it, it's propane nitrile. E's importance as well. Yeah, so you'll probably have forgotten about nitriles by next year, but you will cover them again. Now there's just one more nucleophile to cover, and that one is ammonia, which is slightly different. For a start, it's not charged, and also we have an extra step in this one. Right, so let's do this. We'll start with bromoethane again. CH2, we only need at the moment, we only need the carbon Br bond. We need ammonia. Notice it's not charged. Doesn't stop it being a nucleophile though, because it's got a lone pair that it can donate. Dipoles the same. Organic chemistry is very repetitive. Right, so now we make a bond with the nitrogen and the carbon, and we break the carbon-bromine bond to substitute the ammonia in. And what we get is, it's a bit different this time, CH3, CH2, but this time I'm going to have to draw some extra bonds because there's one more step. Now, as you can see, 2 things. The nitrogen has got 5 bonds attached to it, and nitrogen is only in group 3. And it's contributed more than its 3 electrons to covalent bonds. And also, there is no net charge on the left. So let's finish it off. This is going to have a positive charge on it. All we need to do now is to lose 1 hydrogen, so the nitrogen's only got 3 bonds. And that's going to give us H+. And Br-. You can put them together if you want. So now a hydrogen has gone. I'll put that below here. So now we've got what's called an amine. We need to do a little bit more on amines in the next video, and we also need to look at this bond strength, but that's for the next video. And obviously we've got an H+ come off. Now the bromine's still hanging about, obviously, so that'll just go with the H+. So that's nucleophilic substitution for AS. You'll do all sorts of different mechanisms in the second year if you're in AS, and I will be making videos about those. And in the summer, we will be going through past papers online. I'll get them on the screen and I'll annotate them. I'll do one of each module, and it should be good. Anyway, if you like this video, please press the thumbs up, and I'll be very grateful. I will see you in the next video. Thank you very much for watching, and bye.